Hey guys, welcome back to our channel Logic to Code. So in this video I'll be talking about bitwise end of numbers range. So in this problem we have given two integer m and n, and m and n can vary up to 10 to the power 9. So you need to tell the bitwise end of all the numbers from m to n, right? So this is the test case. So m equals to 5, n equals to 7. If you add all the number from 5 to 7, you'll get 4, and similarly from 0 to 1 you'll get 0. So by looking at this problem statement, you can just think of a naive solution to do the bitwise end of all numbers from m to n using a for loop, but it will give a TLE because the difference of m and n can go 10 to the power 9, so the complexity is O of 10 to the power 9, and which cannot be submitted in 1 second, right? So you need to optimize this solution. So how we are going to optimize this solution? So we'll be using the basic property of bit manipulation here. So once you write the numbers in the binary representation, I have written from 0 to 7. So the one property that you can observe here is that so here the number can go up to 10 to the power 9, so we can store all these numbers in 4 byte, right? So which essentially means we have 32 bits for each numbers, right? So if you write all the numbers from m to n, so we'll have maximum 32 columns. So this is the first column, second column, third column, and similarly we have 31st column, right? So I'm calling this as the 0th column, first column, second columns till 31st column, right? So now observe something in each column. So if you go in the 0th column, you'll see a pattern. The pattern is 0 1 0 1 0 1. So 0, then 1, and then it's repeats, right? Similarly, once you go into the first column, we have 2 zeros, then 2 1, then again 2 0, then again 2 1, right? Similarly, in the second column we have 4 0 4 1, right? So which means that if the column number is I, then the pattern is repeating like 2 to the power I number of 0, then 2 to the power I number of 1. So if you go into the second column, we have 2 to the power 2, which is 4 zeros, then 4 1, right? And similarly, let's say we have in the fifth column, we have 2 to the power 5 0, then 2 to the power 5 1, and so on and so forth, right? So that you can observe from this representation, right? So we'll be using this property to find the bitwise end of all the numbers. So now how we are going to evaluate the result is that, so we'll evaluate all the in column wise manner, right? So we'll see that what would be the value in the 0th column after adding all the number from m to n. Then we'll see the value of the first column from m to n, right? So now one thing you can observe is that if the difference of m and n, let's say 2, right? If the difference of m and n is 2, right, or 1, then we'll get 0 in the first column, in the 0th column, right? So if you take this number, only this number, so let's say m and n both are let's say here what I'm saying is that let's say m equals to what, which is 3, and n equals to 3. So in this case the difference of m and n is 0 because these two numbers are equal. Then we'll get 1 in the 0th position, right? Because there is only one number, so we'll get 1 in the 0th position. Let's say m equals to 3, n equals to 4, so the difference is 1, right? Here the difference is 1, which means we'll get a 0. We are always going to get a 0 in this number. So you take any two consecutive numbers m and n, so you're always going to get a 0, right? So if you take 1 0 or 0 1, right? And let's say if the difference is greater than 1, then surely you will be getting the value 0 here, right? So in each column we are going to get exactly one value. So either I'll be getting 0 in the 0th column or 1 in the 0th column, right? Similarly, in the first column, either I'll be getting 0 or 1, right? So what I'm saying here is that, let's say if the difference of m and n is greater than 1, then we are always going to get the 0 in the 0th column, right? And why I'm saying the difference is greater than 1, by using the same property that this pattern is repeating by 2 to the power I, right? So if you look at in the in the first column, right, we have 2 0 2 1 and 2 0 and 2 1, right? So now my claim is that if the difference of m and n is greater than equals to 2 to the power 1, so column is 1, so we'll 2 to the power 1 greater than 2 to the power 1, then we are always going to get 0 in the first column, right? So we'll take any two number. So we take any two numbers, so that let's say the m is x and n is x plus 2, right? So the difference is 2, right? And the difference can even go larger than 2. So I'm going to say that if the difference is at least 2, then we are always going to get a 0 in the first column, right? And why is the case? So if you take any two consecutive any consecutive numbers whose difference is 2, then you are always going to get 1 0, right? So let's say this could be either this number or this number. You take any number whose difference is 2 or even more, then we'll always going to get the 0, right? And we can just like extend this property. So what I'm saying is that, let's say let me explain with the code itself. So let me make a variable result. So in the result I'll be having 0. So this essentially would be the result of adding all the numbers from m to n, right? So as there can be 32 columns, so let me write a for loop for 32, right? So now what else I'm saying is that if the difference of n minus m is greater than equals to 2 to the power I, which means if this is the case, then we are always going to get, let me just typecast it so that it cannot overflow. So if this difference is greater than 2 to the power I, then my claim is that you are always going to get 0 in the ith column, right? And if it is less than this, then we are not sure about it. So we'll look that after this condition. So my only claim so far is that if the difference is greater than equals to 2 to the power I, then we are always going to get 0 in the ith column, right? So how we are computing the result? We are computing column wise, right? So maximum we have 32 columns. So in the ith column, if the difference is greater than 2 to the power I, we are always going to get the result. So how we can update this in our result is that, so we'll just OR with 0, right? And let's say if this difference is not greater than 2 to the power I, then it would be less than 2 to the power I, right? So now I have to check that what is the exact ith bit of n and m, right? So how we can check that? We'll just do an AND of this. So this will essentially give the ith bit of n, and now let me also check the ith bit of m, right? And just do a AND, right? Just do AND. So if this AND is 1, which means that we are going to get 1 in the ith column, right? So why I'm saying is that if the difference is greater than 2 to the power I, then we are always, let's say these are the blocks of 1 and blocks of 0, right? So in a particular column we have some block of 0, then some block of 1s, then we have some block of 0, and this pattern repeats, right? So if this is the case, then n and m are in the different blocks. So n will be in the 0th block, m will be in the 1th block, right? So that is why we are getting 0, right? So, and if this is the case, which means that the n and m can lie in the 1th block itself. So these n and m can lie in the 1 block itself, or other case would be n and m can lie only the 0th block. So n can be here and m can be here, right? and the third case would be n can lie in the 0th block and m can lie in the 1th block. But if the AND is 1, which means that the ith bit of n and m is set, right? So in this case we know that we are going to get 1 in the ith position of result. So how we are going to update that? What I'll do is that I'll just OR result with 1 left shifted by I bit, right? So this will place the ith bit of result as 1, right? And if this is not the case, so we only have 2 possible cases. So after this case we have only 3 cases. So what are the 3 cases? The n m n can lie in the 1th block, which means n and m will be in this 1 block, right? So it would be like, so if I am writing in the row wise, but it's actually in column wise. So we have some pattern 0, some pattern 1, then we have 0, then we have 1, like this, right? In every column, right? So what I'm saying is that, so this 0 and 1 will be equal. So what I'm saying is that, so if this is not the case, then we have 3 cases. And what are all 3 cases? So n and m can lie in the 1th block. So we have, I'm calling this as the 0th block, 1th block, then 0th block, right? So n and m can lie in the 1th block, or nm can lie in the 0th block, and the third case would be n lie in the 1th block and m lie in the 0th block, right? And let's say if the ith bit of n and m are set, then we are always going to get the ith bit set in the result. But if this is not the case, then we are always going to get as 0 in the ith position, right? And we can update the ith bit as 0 of result like this, right? And at the end we'll just return this result, right? So that's it. So this code should work. So let me just run this code. Yeah, it works on the test case. So let me just submit it. So it's taking some time. So in the meanwhile, if you have any doubt in this question, you can just rewatch this video and do a dry run by yourself, and then you'll be able to understand this. So the complexity of this solution is O of 32, because we are only having a for loop which runs for like 32 times, right? So the complexity is O of 32. But if you apply the naive approach, then the complexity is going to be O of 10 to the power 9, right? So this is the benefit of using the property of bit manipulation. So that's it for this video. So it's still running.